So here we have a picture of a Smith chart, just so you're familiar with it. And the goal of today's 55 minutes is just for you to understand what this figure represents and then how to use it to do some basic calculations. For a big picture understanding of the Smith chart, what the purpose of this diagram is to be able to visually compute the interaction of complex impedances used in transmission lines and other RF circuits. It is, as you can kind of tell by looking at it, it's composed of overlapping circles, and there's these circles here, and then there's these circles here, and so we can kind of see that there's all these intersections of concentric circles. And these intersections of circles represent the real and imaginary components of impedances, meaning that they represent, a complex number of resistance plus a reactance. So we've got, and every intersection of two circles on the Smith chart represents a complex impedance. So we've got Z equals R plus JX. This is, of course, the resistance, and it is the real portion. And X is, of course, the reactance. And it is, of course, the imaginary portion of a complex impedance. We'll see that a Smith chart can also be used to plot admittances, and admittance just being the inverse of the impedance. So the symbol we use for admittance is Y. It is conductance plus J times B, where B is the susceptance, and that is just equal to 1 over Z. It is not true that G is equal to 1 over R, and it is not true that B is equal to 1 over X. So don't make those mistakes there. We have to use complex math to solve for the values of G and B. A little bit of an aside. As an example, let's just say let's have a Z equals 3 plus J4. So Y would just be 1 over 3 plus J4. To do that math by hand, you need to convert 3 plus J4 into a magnitude and an angle, and we've shown how to do that now. It's 3 squared plus 4 squared at an angle of inverse tangent of 4/3, being sure to keep track of what quadrant you're in there. Anyway, if you were to determine the value of that, you're going to get 0.12 minus J 0.16. And if we were to do it this other way, using these formulas, which is not the right way to do it, we would get Y is equal to 1 over 3 plus J 1 over 4, which would be 0.33 plus J 0.25. We notice that they're not the same numbers, this being the correct result. So just make sure you're aware of that, right? So getting back to the Smith chart, we've got these circles here that represent resistances, and we've got these circles here and here that represent reactances. And a Smith chart can represent any reactance and any resistance in the world, any combination of resistance and reactance. However, to do that, we have to use what are called normalized impedances. And that means that the impedance at every point has been divided by the characteristic impedance of the transmission line that we're going to analyze. So when we're doing that, we say the normalized impedance Z, and that's a lowercase z, that's going to be equal to whatever the Z of the system we're looking at, where that's uppercase, divided by the characteristic impedance of the transmission line. So that is equal to R plus JX, whatever the impedance is, divided by Z0. It's generically, we'll write that as a lowercase r plus j lowercase x, and these are normalized. So what does this mean in practice? It's actually pretty easy. Let's normalize a ZL of 40 plus J20 to a characteristic impedance of 50 ohms. So to do that, all we would do is take ZL divided by Z0. That gives us our lowercase z, our normalized impedance, is whatever impedance we're interested in plotting on the Smith chart. divided by the characteristic impedance of the transmission line that we're using. So this is just going to be 40 plus J20 divided by 50. And in this case, we can just divide both those numbers by the denominator, and we get 0.8 plus J 0.4. Note I'm not going to write any units here because I've divided ohms by ohms, so it's unitless. And so this here is R, and 0.4 is X. So that's the first thing you need to know about Smith charts. It's fundamentally a plot of impedances, and they're normalized. And in our case, that's normalized to the characteristic impedance of the transmission line. So let's look at the derivation of that a little bit. On the Smith chart, the real part of an impedance, R, or a normalized impedance, it's represented by these series of concentric circles, and they all have this common intersection point at the very right-hand side. A real line here bisects all the circles, and so any circle that intersects with the this real line, any point falling on that real line, it's purely real and has no imaginary portion. The concentric circle that passes through the middle of the transmission, or the middle of the Smith chart here, it has a normalized resistance of 1. Circles intersecting the real line to the right of the middle point have a normalized resistance larger than 1 and get larger as you move to the right of the line. So you can see we go from 1 here, and if there was a circle small enough here, it would have a normalized resistance of infinity. And if we go in the other direction and look at the circles that intersect the real line to the left of the middle point, so if we're moving from here into this direction, they have a normalized resistance smaller than 1 and gets smaller as you move further left. At the extreme left, we have a normalized resistance of 0, which corresponds to a short circuit, and at the extreme right, we have a normalized resistance that corresponds to infinity, which means an open circuit. So what you really need to take away from this is that any 2 points that are on the same circle have the same real component of the impedance. So if I were to take this circle, well, let's go with 1. If I were to plot any point on the Smith chart, if I were to plot that point, and that point, those all have a normalized resistance of 1. And that's what these concentric circles tell you. You may have noticed that when R is equal to 0, there's this full circle that goes all the way around the Smith chart, forming its own perimeter. So this circle here, since R is equal to 0, this circle is a unique case of resistance, and it represents an impedance that is purely reactive, meaning that the real part is 0. So if we have a point that falls on this line here, it's purely resistive. If we have a point that falls on this circle here, it's purely reactive. Also on the Smith chart, the imaginary part of an impedance is represented via a series of concentric arcs. Arcs that occur above the real line, so remember this is the real line, arcs that occur above the real line represent positive imaginary components, and arcs that occur below the real line, so these down here, represent negative imaginary components. If the Smith chart is being used to represent reactance, the top half of the plane is inductive and the bottom half of the plane is capacitive. If, on the other hand, the Smith chart is being used to represent susceptances, the relationship has to be inverted. What you'll notice is that the closer that the arc is to the real line, the smaller the impedance or the susceptance value that line represents. So on this chart that I'm showing here, the 2 arcs closest to the real line it's hard to read off this slide, but if you were to look at the notes I provided you, these 2 arcs have a value of 0.1. That's got a value of plus 0.1, and this arc here has got a value of minus 0.1. The 2 arcs furthest, here and here, they have values of impedance and susceptance that are 50. Different Smith charts are going to have different amounts of gradation. So some Smith charts may be gradiated more, some may have less. But the overall pattern, that susceptance is going to increase the further away we get from the real line, and it's going to increase the further away we get from the real line, and resistance is going to increase from 0 to infinity with a normalized resistance of 1 directly in the middle of the Smith chart. That pattern's always going to be the same. It doesn't matter what Smith chart you are using.